right, so we're going to talk about linear ODEs. So once we have stuff linear, life gets easier. Okay, we'll talk a little bit about Bernoulli's equation. We'll do a little bit of population dynamics, but mainly we're going to try to solve linear. And so if it's linear, if it's first order and linear, it has this form. Okay. And that means y prime is equal to some function of x times y equals to r of x. Okay, so if, and then here, if it's homogeneous, we say there is no r of x here, and it's just equal to 0. And so homogeneous things are things in mathematics often are things just equal to 0. So here we want to solve this using the fact that if it's homogeneous, it's indeed separable, right? Because if it's separable, let me show you what I'm talking about. This is homogeneous. We're going to try to solve this. This is y prime equals to minus p of x y, right? Just minus that across. And then here I'll have 1 over y dy is equal to minus p of x dx. And then I can just integrate both sides, right? So here I just integrate both sides. So that leaves me with ln of y equals to minus p of x plus c. And then here, if I solve for y, I get y equals to c equal to e to the minus the integral of p of x. Oops. Hold on. Let me back up. C e to this minus integral of px dx. Okay. So no matter what px I give you, whatever function of x I give you, you know what the answer is. It's just y equal to this, right? Because I can always solve it by separating the variables, right? Well, now let's do this one more time. Now we're going to solve a non-homogeneous one using integrating factors, right? And so now that I've taught you how to do two things, so let's just say f is an integrating factor. I'm not going to explain what it is. I'm just going to say it is one. You're just going to have to buy me what it is. I'll prove what it is in a second. Let's just say I start with one. F is an integrating factor. I'm just going to start with one. So f is an integrating factor, which makes this exact. And so here I'm just going to multiply it across here. F of y prime plus p f y equals f of r. Okay. Let's see if I can do this without getting everyone confused. And what do we want? Let me explain what we want. We want, this is why I did what I did, right? So I want f of y prime. So if here, I want to be able to recollapse this, right? And let me explain why I want to be able to recollapse this. Let me wander a journey with you for 1 second. So here, I want that f of y prime equals f y prime plus f prime y. And the reason I want this, because if I can do this, I can collapse this, right, into just f prime y and then just integrate. That's what I want to do. So what does that mean? Well, that means I want p of f equal to f prime. Because here I have p of f, right? And so this is what I want. But this itself is a differential equation. This is a differential equation, and we've seen this before. We know what the answer becomes, right? This becomes, the answer is f is equal, because here I'll have, if I solve this for f again, right, what is f? F, so I have p equal to 1 over f prime. And then here I just integrate both sides. And so I'll have ln of f equal to integral of p dx. And notice p is already a function of x, so I can do this integration, supposedly. Here, in this case, we don't need the c. It's just not necessary, so we're going to leave it off. And so here I get f is equal to e to the integral of p dx. And so here I've declared what my integrating factor is. It's this. So if I multiply that, here if I have e to the integral of p dx times y prime plus p, the integral of p dxy equal to e to the integral of p dx r, I'm leaving off the x's here. I can now solve this because this collapses into this as desired, right? E to the p dx times r. And then here, just to solve for y, is you integrate this, and then you divide by this. If you didn't completely follow this, don't sweat it. I just kind of wanted to show once where this came from. And we're going to get into just what we call boring calculations. And so here we get our final solution. Please say I type this all up in the next page. Oh, good. All right. So here, if it's linear, hold on. If it's homogeneous, we can solve it by separating equation. If it's non-homogeneous, we can use this method to solve it. Now, is this always going to be the same no matter what it is? Yes. And so once it's always the same, let me leave that up for 1 second for you to copy. I'll show you what it turns into. You know, we actually might finish these. All right. So let's go ahead and do the next page. All right, so what does this turn into? So we want to compute integrating factor. So we're going to compute this integrating factor for a non-homogeneous. We're going to compute this, f of x. We're going to write that then. Then we write the solution. We write out the solution, and then we solve it. So once I've done all the hard work for you, which I don't think your book actually does. I don't remember if your book does all this fun hard work for you. Yeah, it eventually gives you something like this, so it just doesn't write it down so nicely. Anyways, so once you've done all this hard work, it's a two-step problem, right? So here I have a non-homogeneous differential equation, right? Which is non-separable, right? Because you have t's over here, and you can split the y's and t's. You're just not going to win, right? So it's linear in the sense that I have y prime equals some function of t. And, oops, this should be a t if this is going to work, right? Some function of t and then another function of t. So in order to solve this, we're going to do the following. We're going to do step 1. I'm going to show you now that I've done all the hard math. The actual calculations aren't too bad. So here we're going to have f of t. F of t, because if it's x, here it's going to be t. F of t is equal to the following. E to the integral of 2 over t dt. So this is equal to the integral of e to the ln of 2 ln of t, right? That's how this what the integral comes to. Here, I can switch this to e to the ln of t squared. And so this is just equal to t squared. So my integrating factor here, all I'm doing is taking the integral of 2 over t and raising it to the power of e. Well, 2 over t is just ln of t times 2. Put that up so I can clear out my things and I get t squared. So that's what my integrating factor is.
Excuse me?
Yes.
How do we know what to put in the integral? Is it just whatever is next to the y?
Yeah, whatever's next to the y. So it's always going to come in this form. So you're going to have y prime with nothing on it. If there's something on it, just divide it out, right? Just divide it out. And then if it's linear, this will be only a function of x, and this will only be a function of x, and we only have a singular y here. If this is y squared, it's not linear, and you cannot use this method, right? If this is a function of x and y, you cannot do this, right? However, these non-homogeneous comes up all the time. So even though it is kind of a niche, it's a very common one. So here, you just always just take what's right here, crunch it through. Then the next step is you write down the answer. Y equals 1 over f of, in this case, t, so 1 over t squared, the integral of here of t squared, rx, well, rx is right here, so it'll be t plus 1 dx plus c. Please, please, please understand that this plus c is multiplied by this function. Okay, this is very, very important. All right, so let's compute the integral. So I have 1 over t squared. This becomes t cubed. So t cubed, so the integration of that is t to the 4 over 4. This becomes t squared, right? And that becomes plus t cubed over 3. And then we have our plus c here. And then we just distribute t squared. So I get t squared over 4 plus t over 3 plus c over t squared. So notice that the c can eat any constant, but it cannot eat a variable. It's not strong enough to take on the variable. It's just not. And so we have to leave it like this. Okay? So when we divide out the t, we get this. And this is our answer. That's all you have to do, right? Let me show you again. Let me zoom out. So here's step 1. Is this linear? Yeah. Well, I have y times some function only of x equals something only of x plus y prime. So yeah, this is linear. So let's go ahead and go on and do this. So our first step is to find f of x in this case. We're in x, my integrating factor. My integrating factor is the following. E to whatever's on my y, integrated, tan x dx. Well, the integration of tan x dx is equal to e to the ln of secant x. Well, the ln of secant x cancels out, so you just get secant of x. So step 2, y is equal to 1 over secant x, because that's what my integrating factor is, times f times r. So here would be the integral of f, which is secant x, times r, which is sine of 2x, dx plus c. Let me put this all in parentheses. We crunch through this, so here I get 1 over cosecant, or secant of x. Hold on, let's just make that 1 over secant of x is just cosine x. Just make our life easier. This integral, see if I can make my life even easier. This is 1 over cosine x. This sine of 2x becomes 2 sine of x cosine x. I can cancel this off, so I'm just left with 2 sine of x dx plus c. Let me just do that. So here I have cosine of x the integral of 2x is, of course, just minus 2 cosine, or 2 sine of x, 2 cosine of x plus c, which just equals minus 2. Let's go ahead and move that in. Minus 2 cosine squared x plus c cosine x. And this one has an initial value. And so here, when y is, so this will be step 3. When y is, when x is, y is equal to 1, when x is 0. So here it'd be minus 2 cosine squared of 0 plus c cosine of 0. Well, that implies that c is equal to 3. And if c is equal to 3, we can write out our final answer, which will be minus 2 cosine x squared plus 3 cosine x. And I'll leave that for you guys. All right. So if it's linear, you should be able to solve it quite quickly, actually. If it's homogeneous, the answer is just y equals c to the e to the minus px, right? You just do this and you pump out an answer, you're done. If it's non-homogeneous, you go ahead and just follow this right here. You calculate what this is, and then you just crunch it through. And so what makes this wonderful for engineers is it's very formulaic, right? Just crunch number. That's it. Okay. All right. I think we should be able to get done. Let's just do the next one. Yeah, so let's do something a little bit hard. And then we'll go do something a little bit easier. All right, so let's look at Bernoulli's equation. All right, so reduction to linear form. So Bernoulli's equation. So Bernoulli's equations look like the following. Here I have, it looks a lot like linear, but instead of having this, I have this little troublesome thing right here. So, so if it's 0, if a is 0 or 1, it's linear and you can solve using the other method. If it's not, otherwise let u equal to y of x of 1 minus a. And the reason I do that, because u prime turns into this, this, and this. I'm going to skip the derivation. We've done a lot of derivations today. Just because Avery's a little short on time. So here, u prime, and this is, I mean, you can calculate this directly here. This is just total differentiation here. I do my y, and then what's inside my y and y prime. Mess with stuff for a hot minute, and then I get to this. This is now linear, right? This is some function, and this is some function. Notice here I've gotten rid of all my y's. Because remember that g, p, and g right here are functions only of x. So this is only of x, and this is only of x. And so now this is linear. And let me just show you via an example. So here's the Bernoulli equation. I'm not super familiar with it, but some of you might be. Anyone recognize the Bernoulli equation? I don't even know what it's for. Bernoulli's first holes. Oh well, I'll look it up later. I'll look it up while you guys are writing it down. So here, let's do this. So in this case, notice here, what is my A? Here, here for my, here I have a equal to, let me rewrite this. So I have y prime minus a y equals to minus b y squared. Okay, so here I've just rewritten it. Now it looks a lot like this, where this is a and this is b, where a and b are just constants right now. So these are constants. So here we're going to let our a equal to 2. Because if our a equals to 2, we can rewrite this equation using the following, right? U prime plus 1 minus 2, and p here is just a. Oh, no, p here is minus a, sorry. Minus a. So 1 minus 2, p, which is minus a, equals 1 minus 2, g, which is in this case minus b. And here I put a u. And we're just going to solve this. And if I simplify this, this is just negative 1 times 1. So this is plus a u equal to b. So here I just have this very simple. This is now linear. It's now linear. So we're just going to run through our steps. Step 1, f of x is equal to e to the integral of a dx, which is just equal to the integral, or is equal to a x. Since this is just a constant, just e to the ax. So step 2 is u equals to 1 over my f, which is e to the ax, integral of e to the ax times my r, which in this case is b, dx plus c. All right, so let's crunch to this. So this means u is equal to, I'm going to write this up top. So it'd be e to the minus ax. Well, here's the integral of e to the bx of ax times b. Just b over a e to the ax. So if I integrate this, I just divide by a plus c. And so this implies u equals b over a, this cancels, plus c over e to the ax. Any questions on how I got to this point? Here, let me just make sure I'm clear here. Here, I took this and put it into a linear form. Then using the substitution where a is 2, right? I produce this, which produces this very simple linear equation. Then I'm just solving it the same way as I did before, and I get this. Now I have to say, well, what is y? Well, remember here, u of x is equal to y of x of 1 minus a. Well, a here was 2. And so u equals to y to the negative 1 power. That means y is equal to 1 over u. And so if I figured out what that is, so y is equal to 1 over b over a plus c over e to the x plus a. Okay. Because y is equal to 1 over u. And so I just take 1 over this, and this is our final answer. All right, I'll let you write that down. Simplify. Do we have to? I mean, you could simplify this a little bit more, but it doesn't get too terribly much more simpler than that. I mean, you can move the c up top, but b over a plus a over c. I mean, technically you could write that all as negative 1, but it's not that much. right, so the last little thing I want to do is talk about autonomous equations. Because these come up in population dynamics all the time. So let me just show this. So here, so an autonomous equation is as follows. So here it's just y prime equals f of x. And so this is even simpler than a linear solution. And so what we can have here is what we call equilibrium solutions. And equilibrium solutions is where our function is where f of x equals, hold on, I wrote this wrong. This is f of y. And our equilibrium solutions, where f of y, I had it right here, where f of y is equal to 0 are called critical points, giving constant solution called equilibrium solution, equilibrium points. And so here, if I want to find the equilibrium solutions and state what they are, here I'm just going to figure out where this is 0. Well, the equilibrium solutions here, I just call them EQ solutions. That's y equal to 0, 1, and 2. And so let me kind of explain how you can graph this by hand, and then I'll show you in the computer, and then we'll be done. All right, so here, let me use red, just so I can rewrite stuff. So here, I have a solution here at 0, another one at 1, and another one at 2. So here, we have a solution at 0, 1, and 2. This is our y, this is our x. Notice here that the derivative here has nothing to do with y or x, right? Or has nothing to do with x. So how do we know how the solutions will behave? So once they hit the solution, they will not, once it hits the 0, once the derivative is 0, it stays 0, right? Because nothing's going to move it. And so here, these are equal, so the solution stays 0. Why? Because if I have this to be 0, is my y ever going to change? No, my average rate of change is 0. That's what the derivative means, right? So if this equals a 0, it's never going to move from that, so it's always going to stay 0. So that's what it means to be an equilibrium solution. Now, if this is an autonomous one, it's always going to be constantly going up or down. And the way we figure that out is we just plug in a point, right? Y of 0.5. Well, 0.5, let's just test this real quick. This is positive, this is negative, this is negative. And so overall, it's a positive, negative, negative. So overall, it's going to be positive. And so solutions in between here are going to tend upwards, right? Here at 1.5, this is positive, but this is negative. And so solutions are going to tend downwards. Here at y equals to 2.5, just something above it, this is positive, this is positive, this is positive. Oops, all right, that should have been negative. And so here, all the solutions are going to tend downward. And then here, at y equal to minus 0.5, this is negative, this is negative, this is negative, so they're going to tend downward. And so what we have here is now I can kind of guess what the solutions look like. Here, solutions starting here are going to just slowly decrease. Solution here are going to come, they're going to increase to this line and then level off. Solutions here are going to come, increase to this line and level off. And solutions here are going to expand outward for infinity. And so we're just going to label these real quick. So notice here, solutions around this point around this equilibrium point tend to come towards it. So we're going to call this one stable. This is a stable one. Solution around this equilibrium point tend to be unstable. And the same here, unstable. And in fact, let me show you this all one more time in the last 2 minutes. Give me 1 extra minute. And then I can finish this section beautifully. And then we won't have to have it be awful. Oh, where am I? I want my tools. So think about it stable. So if you have a pendulum, right, and you're just swinging it up and you're holding it and it's down while it's down, that's very stable because if you move it off, it's going to come back. But say if you take the same pendulum, flip it upside down and have the weight up top and you're just kind of balancing it, well, that's unstable because the second it gets a little bit off, it's going to want to go a lot off. And so let me show you using this. So let's look at HPG solver real quick. And here I'm going to type in my solution. It's going to be y times y minus 1 times 2. And we're going to show our field. So here's our field. And so let me draw in a solution here at 0. So 0, 0. Let's do a solution. We'll do one at 1, 0. Draw another solution. And then we'll do one at 2, 0. So these are my equilibrium solutions, right? Solutions that are, now if my initial condition was slightly off of this, notice here that it just quickly disappears. And if I'm close to here, notice that these solutions tend, if I'm slightly above or slightly below, they'll tend to 1. And so 1's a stable equilibrium point for this. And then here, this is unstable because if I'm even just a little bit off, it eventually goes away from it. And same thing here, if I'm a little bit off, it goes away. Okay. So that's it. That's it for this section.